It's very happy to have for his second talk. We'll be speaking about the emergence of space and time and holographic duality.
Great. Yeah, thanks very much for that introduction and for the opportunity to give this talk. So I'll talk about the idea of how space and time dimensions, in particular, sort of in the context of holographic theories of quantum gravity, how do these sort of bulk dimensions come out of fundamentally quantum mechanical degrees of freedom? And so this has been something I've been developing with Honglu over the past few years. And I'll mostly talk about this most recent paper from just over a year ago and some upcoming work. Great. Okay, so the setting in which we're going to talk is the idea of this so-called ADS-CFT correspondent, which of course many people here are very familiar with. And so just to get us all on the same page of how I want to talk about this, let me say that what does the ADS-CFT correspondent say? Well, it says that somehow some quantum theory of gravity. So you can imagine sort of schematically on this disk here, there's some theory of quantum gravity. It has some propagating degrees of freedom down there. That theory in an asymptotically anti-de Sitter spacetime. So that's just this anti-de Sitter space is this homogeneous solution to Einstein's equations with a negative cosmological constant. Well, somehow quantum gravity theories in this sort of green disk region here are equivalent to conformal field theories that live on the boundary. So that would be this sort of black circle here. And so this goes back to Maldacena in 1997. And so why is this still an interesting thing to study? Well, one of the nice ideas of this duality is this sort of concrete realization of the holographic principle. The idea that theories with dynamical gravity, they secretly have less degrees of freedom than you would have naively thought that they had. So in this picture, we have this theory that has dynamical gravity in the bulk. So I should say I'll often refer to this sort of the green disk, the gravitating system is the bulk. This particular theory with dynamical gravity can secretly be encoded in terms of a conformal field theory that lives in one less dimension. And another very striking aspect of this correspondence is that this theory that has dynamical gravity in the bulk is some quantum gravity theory, but the boundary theory is a conformal field theory. It's just a regular quantum field theory that in principle this is completely well defined, and we can understand all of the aspects of that conformal field theory. And so in particular, the gravitational physics that we see in the bulk can be treated as an emergent quantum mechanical phenomenon coming out of this boundary field theory here. Okay, so at the highest level, what I've just told you is that there's some bulk gravity theory, and that's equivalent to a boundary conformal field theory. So what should this really mean? Well, a very strong statement of this idea is that for any state in your quantum gravity theory, I should be able to hand you a conformal field theory state, and I should have this one-to-one correspondence between those states. Okay, so let me draw a particular example of this, which was suggested by Maldacena in 2001, which is the idea that in the quantum gravity theory there should be some states whose geometry looks like that describe geometries that look like this eternal ADS black hole, and that quantum gravity state should be dual to what's called the thermofield double state between two copies of the holographic CFT. And so this is just some particular entangled state between these two copies. But what I want you to notice is that the right-hand side, because I've been suppressing all the other spatial dimensions, the right-hand side of this picture is a lot simpler than the left-hand side. It's been well known. It's been well known for a while. Sort of how do we understand operators in the exterior, in either of these exteriors of this eternal ADS black hole from the boundary perspective? But there's a lot more going on in this picture. Many more geometric features. In particular, there are horizons. There are these surfaces that we can't see past with naive constructions from the boundary in the CFT. There's these interior regions, and in principle there should be operators in the bulk that we should be able to understand from this boundary perspective somehow. And there's also this notion of infalling observers. In this bulk theory, I can describe somebody who starts here in the right exterior of the black hole, crosses the horizon, falls into the future region, and eventually hits the singularity. And so what I want to emphasize is that sort of all of these geometric features of the left-hand side, they're not entirely obvious from this very simple picture that we have on the right from the conformal field theory side. Okay, good. So coming back to this idea. Coming back to this idea. Well, secretly, what did I really draw for you here? Here I just drew some entangled state of two field theories, two quantum mechanical systems. But what I drew over here was this classical Penrose diagram of the eternal ADS black hole. And so this has all these nice classical geometric features. And more generally, this picture is really an effective description of the bulk quantum gravity theory. In particular, it's an effective description in the limit that Newton's constant goes to 0. And through the well-known mapping between the sort of gravitational parameters and the boundary theory parameters, this semi-classical limit is actually the n goes to infinity limit of the boundary CFT. And so here, sort of schematically, I'll just use n to parameterize the number of degrees of freedom in the boundary theory, which is going to infinity. Okay, and so it's in this semi-classical limit that these quantum gravity states sort of admit this effective description in terms of the classical geometry and some quantum perturbations around that geometry. And that means that somehow the features of that classical geometry must be features of an n equals infinity CFT. So whatever that means, and we'll spend some time talking about how do we define what we mean by this n equals infinity CFT. And the generalization of the questions of the features of the geometry of the eternal black hole geometry, they can be sort of stated more generally in different settings of the correspondence. That we'd like to understand, where do space-time subregions come from? How do we describe the idea of these sort of emergent bulk space-time subregions from the perspective of the boundary theory? In particular, of particular interest are regions like the interior of the black hole, which are not sort of obviously described by any sort of subregion of the boundary theory. Another thing we'd like to understand is how do event horizons of the dual geometry, what's their signature in this conformal field theory? How do we understand? How do we know? How does somebody hand us conformal field theory and the thermofield double state? How do we know if there's an event horizon or not? So that's another question of interest. And the other sort of very interesting question is, what's the experience of an infalling observer? How do we construct notions of time that will take that are similar to the proper time of an infalling observer, somebody who starts in the exterior of a black hole and crosses the horizon into the interior? How do we construct those from the boundary perspective? Because the duality tells us that those things should be there. Okay, so these are sort of the big questions that we've been trying to answer from the perspective of studying this large n limit of these holographic conformal field theories. And today I'm going to focus on the idea of space-time subregions. But let me also say that we have a proposal for how to probe this sort of event horizon from the perspective of von Neumann algebras, and a proposal of how to probe these infalling times from a particular algebraic structure called a half-sided modular inclusion. I won't talk about those today, but if you have questions, let me know after the talk. Okay, so ultimately, what I really want to understand is that we have all of these geometric features of the bulk geometry that should be coming out of this conformal field theory somehow. And so the big question and the title of the talk was basically, how does the bulk space-time emerge from the CFT? And so this is a question, I think, of general interest in this community. And I want to change the question a little bit to be a bit more precise and ask, what's the mathematical structure of the CFT that allows it to describe these geometric objects in the bulk? And what I'm going to argue is that bulk spacetime is a geometrization of emergent type 3.1 algebras on the boundary. Okay, so this is the slogan. It's a little bit complicated. So I'll try to spend some time, the rest of the talk trying to convince you of what this really means. Roughly, what the idea is that the structure of the conformal field theory, in particular, if we look at the operator algebra content of that theory, undergoes many changes and transitions when we take the n goes to infinity limit. And the structure of algebras and local algebras of the theory that we can define in the large n limit is very strange from the boundary perspective. So I get all of these sort of strange features of algebras, of the algebras that are assigned to local regions in the large n limit. But if we can define the duality between these more abstract boundary algebras and bulk regions in a certain way, then it turns out that the bulk geometry sort of gives a natural understanding of why did these operator algebras have such strange features from the boundary perspective. So in this sense, the geometry emerges from the algebraic structure on the boundary. And that's what I'm going to argue. Also, as an aside, these various geometric notions can be related to properties of these emergent type 3.1 algebras. So as I mentioned, we can talk about the idea of horizons. We can talk about the idea of infalling times in the bulk geometry. Both of those are necessarily require these type 3.1 algebras for a sharp definition. And in particular, the reason this word emergent is there is that those are type 3.1 algebras that were not there at finite n. They only appear and have this transition when we try to seriously discuss the large n limit from the algebraic perspective. So I'll pause for a moment if there's any questions right now before I do my outline.
So do they have a counterpart of finite n that's
so
here or?
So the properties at finite n their properties are quite different at finite n, and what we'll see is that the real power of ADS-CFT in this setup is that we sort of know how to define those local algebras at least abstractly. We know how to define those algebras at finite n, and we know what their properties should be, and we'll see that there are sort of different ways to take the large n limit. And if you do it in a way that remembers some of those properties from finite n, then you'll get sort of algebras with different properties that probe different regions of the bulk, compared to a setting in which we sort of throw out any memory of the finite n theory and the properties there, and then try to discuss it, and then try to localize after we've taken n to infinity.
But this is like the strict.
Yeah. So everything that I'm going to talk about is in the strict n to infinity limit, and different ways of approaching that limit from the algebraic perspectives. But in the end, all of the results are at the n equals infinity.
Is there a sense in which you can identify some approximate stuff for n, which is finite?
Yes. So I think there should be a sense in which the approximate things hold true at large but finite n. The key though here is that I'm going to be talking about algebras that are sort of closed undertaking limits and stuff like that. And so to really close the algebra undertaking limits without having something very strange happen, I do need to be at n equals infinity. And so it's because I'm demanding this algebraic structure. Now there might be sets of operators that obey all of the properties that I like, that in the sense that I can't take arbitrary products of them, but maybe just I have a few of those operators, and those will have this sort of approximate notion. So for example, like we can have approximate notions of a horizon, right? Like there's these sort of Lieb-Robinson bounds in systems that outside of certain light cones for local Hamiltonians, we have exponential tails. But what I want to talk about here is where those tails are really zero. And so that's in this algebraic structure we'll see that really is a feature that only happens at n is infinity, just like it's the continuum limit in that example. Yeah.
Do you have a specific type 3.1 algebra in mind? There are a lot of classes of them, right?
So really, what I will describe to you, it's believed. It is believed and to some levels of rigor known that all of these algebras that I'm going to get are the sort of unique hyperfinite type 3.1.
Oh,
Yeah. So it's believed that they're all going to be hyperfinite, but that's from general considerations in quantum field theory. And I won't be able to prove to you that that's the case, but yeah, good.
There's one hyperfinite type 1 factor.
Yeah, there's a unique there's a unique hyperfinite type 3-1 factor. Yeah. Good. Any more questions at this point? Okay, great. Okay, so let me come to the outline. So first, just to orient everybody, and for those of you who are here on Friday, I apologize, this will be a bit of a review. I'll talk about the idea of local algebras in quantum field theory and quantum mechanics, and talk about, in particular, how they're different, what things are the same, what things can we define. Then I want to talk more seriously about how do we take this large N limit, what's the Hilbert space of states that we can define in taking this large N limit. And then I want to talk about the implications of these large N algebras for holographic dualities. And what I want to show you is that we now know how to what we did is we understood how to understand how to describe much more general bulk subregions than previously people had been able to understand. So if you're familiar with it, there's the usual story of what's called subregion duality, which tells me if I have some boundary subregion, what bulk subregion do I have? And what we'll see is that if we use the algebraic perspective, not only can we understand this and sort of get some insights into this, we'll also be able to describe much more general regions of the bulk. Then I want to talk about the fact that these algebras sort of violate this a condition called additivity that I'll introduce later. And that's a feature of the large N limit that lets them describe local bulk physics. And then, I told you that I was going to generalize subregion duality. So I had better be able to do something with subalgebras we couldn't do before. So I'll describe some of those more general cases. And I'll close with a discussion of other applications of this framework. Okay, great. So let's come back to some real review, which is the idea of local algebras in quantum mechanics. So in quantum mechanics, the states of the system are described by some Hilbert space H. Now, if I have access to only some of the local, if I have access to only some degrees of freedom in quantum mechanics, then usually we can imagine we only have access to this HR. Then the operators that I have the ability to manipulate is the algebra of bounded operators acting on those degrees of freedom. So I'll use this sort of script B. This means all bounded operators on the particular Hilbert space of interest. Okay. And then we can ask, okay, well, if I throw out the environment, can I throw out the environment and give it some local description of the physics? And so in particular, if I have some global state in this setting in quantum mechanics, the answer is yes. I have a reduced density matrix that I just take the partial trace of psi over H left, and that gives me a local description of the state that's defined in terms of only quantities in this that are described in this right Hilbert space here. Okay, then I can ask, well, how much information did I throw out by forgetting about the environment or the degrees of freedom that I don't have access to? And that's quantified by the so-called von Neumann entropy, which is just functional of the density matrix minus trace of rho log rho. If for entangled states, this is non-zero, and in particular, it means that I can't locally determine sort of the exact state of the system. There's some sort of mixture of states on the local system that I have access to. Okay, but this entangled setting is very interesting. So when this is non-zero, there's a very interesting consequence in the case that psi is highly entangled. So if this state is a really highly entangled state between the left and the right degrees of freedom, then these reduced density matrices that describe local physics on the right and local physics on the left will be of full rank. And it's only in this case that we can define a particular automorphism of the algebra, called the modular flow. That's just in this type 1 setting is constructed in this way. We just take the density matrix, its inverse density matrix on the other degrees of freedom, raise it to some complex power, and conjugate our operators. The reason this is important, is because this is some automorphism of the algebra that preserves the local structure. So if you can just see this, if I imagine that A was an operator only on these right degrees of freedom, then you can see that sort of the row left to the IT, row left to the minus IT would just commute through and they'd cancel each other. So this describes some sort of local automorphism of the algebra. Okay.
You said local bounded operators. What is that? I mean, in quantum mechanics, operator is not bounded in general, but we feel bounded.
Oh, yeah, right, sorry, yeah, so to make this a von Neumann algebra that's defined on the entire Hilbert space, I need bounded operators. So that would be like bounded functions of local operators, is that, yeah, that's what I would have to do, good. Okay, any other questions on this? Great, okay, and so now let me tell you that there's all this beautiful structure that lets us describe the ideas of sort of, entanglement and local physics and quantum mechanics. And now let me tell you that that's not, we don't have this structure in relativistic quantum field theory. So here I've just sort of pictured a Rindler decomposition of Minkowski space. And so what you would say is you say, okay, well, like, let me just draw the t=0 slice coming through the origin here. And then I say, okay, I have some degrees of freedom on the left, I have some degrees of freedom on the right. And I should associate Hilbert spaces to each of those degrees of freedom. And then just talk about the quantum field acting on the left and acting on the right. But it's sort of a well-known feature that kind of picture is actually inconsistent with relativity. In particular, in relativistic quantum field theory, these localized Hilbert spaces simply don't exist. There don't exist these local Hilbert spaces on which those fields can act. There are not reduced density matrices that describe the physics locally in those regions. And there's no finite, well-defined notion of entanglement entropy for either of these left and right regions without any cutoff put in place. Okay, but what is true is that the modular operator and modular flow, that particular automorphism, they still exist. Okay, so what's the physical meaning of this? Well, what it means is that, okay, we've lost a lot of these quantum mechanical concepts like like tensor product Hilbert spaces and reduced density matrices and things like that. We've lost a lot of that local description in quantum mechanics, but the fact that modular flow exists in relativistic quantum field theory, this is a reflection that all states in the Hilbert space are highly entangled. They're highly entangled between sort of this algebra on the right side and the algebra on the left. And this is a fundamental difference between local operator algebras in quantum mechanics and those in relativistic quantum field theory. And the reason why it's nice to talk about these von Neumann algebras in this way is that these were classified by mathematicians almost 100 years ago by Marie von Neumann. They were classified into 3 different types. And in particular, in quantum mechanics, that local operator algebra, which was the algebra of all bounded operators on some Hilbert space, that's what's called the type 1 von Neumann algebra. And in relativistic quantum field theory, the algebra of operators in the right Rindler wedge, for example, is one of these type 3-1 von Neumann algebras. Okay, and let me say that, the specific nature and the meaning of the types is not super important for this talk. And I talked a lot about that on Friday about what these mean in regards to entanglement structures. But the important point is that in relativistic quantum field theory, local algebras are of type 3-1. In quantum mechanics, they're of type 1. Okay. So that was sort of a digression into the idea of how do we talk about local observables in quantum mechanics and in relativistic quantum field theory, and in particular that there's this nice way to say precisely sort of what the difference is when we try to talk about local physics. Okay, so now let's come back to the idea of sort of large N holographic CFTs. So consider a CFT that has some n by n matrix degrees of freedom. So you might have an example here. You might have, for example, something like, n=4 super Yang mills with gauge group SUN. It has some matrix degrees of freedom going on there. Okay, so at finite values of n, the CFT just has a well-defined Hilbert space, which is the CFT Hilbert space on which all of these operators, these sort of matrix degrees of freedom will act. And if we take the full algebra of operators acting on a CFT Hilbert space, then they'll generate an algebra of operators that's of type 1. So here I'm talking about the full, even though this is a field theory, I'm talking about the algebra of operators everywhere on the boundary space-time. And so if I take them everywhere, I don't restrict to a subregion, they'll generate one of these type 1 von Neumann algebras.
Can you explain a little bit what is the difference between the global and the local?
Oh, the global.
Why is there this difference when you go from the local to the global algebra?
Yeah, why is there the difference? I mean, okay, maybe roughly one way to say it is that, in this, okay, so imagine that you wanted to construct an operator like the projector onto the fifth energy eigenstate or something like that, the fifth highest energy eigenstate. Clearly for any sort of non-trivial Hamiltonian, that projection is going to involve operators everywhere in the space-time. And so if I take limits of sums of products of those operators, of local operators everywhere in the space-time, then I can construct that operator that I wanted, this as a particular limit in terms of those fields. But I really have to have access to the entire space-time to construct an operator like that, like projection onto a particular energy eigenstate. And so when I have access only to a subregion, I can never construct operators like that because locally I don't have any sort of pure states. And that's sort of precisely the difference between the local and the global operators. Did that answer it?
And as long as you have all these projections, it's type 1.
Yeah. So type 1 is actually defined by there exists a minimal projection for a one-dimensional projector. Yeah, good. Great. Okay, right. So this is the story at finite n for the algebra of operators generated by all operators on the entire boundary spacetime. Okay. But what happens if I try? To take n to be very large and take it to the infinity in the end? Whoops. Then what happens is that some states and operators in the theory may not survive the large n limit. If I try to compute correlation functions of heavy operators and in some states, and I try to keep every single operator in every single state. What I'm going to find is that a lot of those correlation functions diverge. And what this means is that those operators, those sort of the operators that I was considering here, these heavy operators, they don't define genuine Hilbert space operators in the strict large n limit. Whenever they act on a state, they're going to give me infinity. And so this is not some sort of genuine Hilbert space operator.
And again, it's divided by n some power and
yeah. So yeah, right. So I guess for the single trace ones, you can put the appropriate n normalization. But for heavy operators, in general, you can't define and to have like all of the endpoint functions of that operator be well defined in the large. Okay, all of the little n point correlation functions of the operator be well defined in this large n limit. Yeah. You can't find such a normalization. Yeah, good. And so the fact that a bunch of operators and states of the theory may not survive the large n limit has dramatic consequences for the structure of the Hilbert space and the operator algebras that can be defined in the strict n goes to infinity limit. Okay, and so coming back to these matrix examples, what are the operators that are well defined in that limit? And so this gives rise to the notion of a single trace algebra. Okay, so let me say, in this theory with these matrix degrees of freedom, at any finite value of n, I have some OPE for these single trace operators, and I can compute things like this commutator. And at any finite value of n, I could choose to do a 1 over n expansion, but this defines for me sort of this state independent algebra. So there's an OPE algebra, and that defines for me sort of like the structure of the CFT. Through the OPE. Okay, good. But sort of crucially, what will happen is that good. And so at finite values of n, you can do the 1 over n expansion, but in principle, there's no reason to, because if n is finite, then 1 over n is not necessarily small in the strictest sense. Okay, good. But if I take some state psi, which is some state, you can imagine this as a sequence of states in many copies of the CFT, taking this parameter n, getting larger and larger. If I subtract off, and so in general, the 1 point functions of single trace operators in such a state, they might be blowing up in the large n limit. But if I shift and subtract off that expectation value, then these subtracted single trace operators will have a well-defined large n limit. There's some normalization in which I can make sense of all of their endpoint functions in this state psi. Okay, and then furthermore, in theories that obey large N factorization, there's this notion of semi-classical states, which means the following thing. That is, I'll call psi a semi-classical state if the following is true about the correlation functions. If I take O1 and O2 to be some single trace operators, and then OR and OL, you can imagine, are just some finite products of other single trace operators. If in computing this expectation value here, if I can replace O1 and O2 by just some constant that I'll call C12, in principle, this constant can depend on the state that I'm considering within this correlation function, up to 1 over n corrections, then we call that a semi-classical state. And the reason that this is important is that, to leading order in 1 over n, these commutators are equivalent to just some complex numbers when I'm careful to be inserting them only in these sort of states that in a sense are close to the state psi that I started with. There's some finite product of single trace operators on the CFT state that I started with. Okay, good.
I'm a little bit confused. Which part of this assumption is non-trivial given what you already wrote?
Oh, sorry. What is non-trivial? Oh, sorry. Yeah. So
The leading order term and the sum is order 1 times another.
Oh, good. Yeah. The thing is that there could be, if for a general state psi. So okay. So in the vacuum, it's totally fine. But for a general state psi, it could be that these lower order terms receive large contributions that grow with n in this state psi, and so I have to actually resum all those contributions, and that's why this coefficient is state dependent. Yeah, good, great. Okay, and so let me emphasize that this is this sort of state independent characterization of the OP algebra that I can give at finite n. But this is a very different notion of algebra here when I truncate the large N expansion. This has really a different algebraic structure. When I say O1, O2 is equal to some complex number, that's a very different algebraic structure, and is sort of highly state dependent. It's highly state dependent, but it's something that I can define in the large N limit. Whereas this is something that is harder to understand in the large N limit. Okay.
So that expansion is not conversion.
Right. Yes. Yeah. So yeah. This expansion is not convergent. Yeah. And so in order sort of to make sense of this expansion, I'm going to insert it in these special correlation functions and only consider it in states that are very close to psi in the sense of being related by a finite number of single trace operators.
So even if the state psi is semi-classical, why should OR apply to psi be semi-classical?
So this
That's what you're really using.
Well, yeah, right. So what I mean here is that OR should be some finite product of single trace operators. So really, right, this is just a string. This is just a string of some finite product of single trace operators in psi. And so all those correlation functions will factorize when I write out OR in terms of a finite product of single trace.
That's the definition.
Yeah, that's the definition. Yeah, good. Great. Okay, so this defines for us a notion of large N algebra, and I want to emphasize it's a very different algebraic structure to this sort of state-independent OPE algebra. Okay, good. And good. So in the large N limit, we can actually define a state-dependent single trace algebra that we'll call A psi. Okay, so that algebraic structure where I've really truncated that expansion defines for me an algebra. I have some relation between the operators. Good. If we act this algebra A psi on the particular state psi whose 1-point functions we subtracted when we were constructing it, it turns out that if I have an algebra and I have a state on that algebra, then there's a well-known construction called the Gelfand-Neymark-Siegel construction that lets us view those excitations as building a genuine Hilbert space, sort of closed under its own inner product. So the structure of small excitations about this state, the set of states of small excitations around the base state psi actually can be closed to form a genuine Hilbert space. Okay. In this genuine Hilbert space, there's something called the GNS vacuum state. There's in a sense a preferred state, which is just the state whose correlation functions of the representations of operators in this state exactly reproduce the correlation functions of the single trace operators in the state psi. Okay, and so all of this is to say that this H psi, this GNS Hilbert space, is furnishing a representation of this sort of abstract single trace operator algebra. And I'll denote that here by M psi. And so pi psi is the representation. It takes this abstract algebra and writes them as explicit operators on this GNS Hilbert space. And what I've drawn here, this double prime will come up a couple of times. All this is saying is that this algebra itself may not be a von Neumann algebra in the sense that it's not closed in the appropriate topology. And what this double commutant operation does is close it into a von Neumann algebra. Okay, so what is the double commutant? Well, okay, the single commutant is that I just take a set. I have some set of operators. The single commutant says, give me all of the bounded operators that commute with all of the elements of that set. That defines the single commutant. The double commutant is that you just do it again. And so now it's a general theorem called the von Neumann double commutant theorem that if I do this operation, it always gives me a von Neumann algebra that's closed in a particular topology. Okay. Good.
Where did you use single trace? It was in the asymptotic expansion, or it was in the definition of the semi-classical state?
Oh, yeah, in the definition of the semi-classical state, so that I get that factorization.
Because
Yeah.
otherwise it wouldn't factorize.
Otherwise, it wouldn't factorize. Exactly. Yeah. Good.
What's the difference again between psi and like the vacuum?
Oh, yeah. Okay, that's a technical point. I probably should have removed psi. I want to imagine as the CFT state. It's really a sequence of CFT states in each, as I'm increasing n in my family of CFTs, as I'm increasing n to make it larger and larger. And then 0 psi is an element of this GNS Hilbert space here. It's sort of a vector state in this actual GNS Hilbert space. That is morally, it's just the representation of this CFT state in this GNS Hilbert space of small excitations. But it's really more of a technical point. Yeah. But yeah, if you read the sort of Gelfand-Neymark-Siegel things, then they always give you this so-called GNS vacuum, which is just the state that realizes the correlation functions that you used in the first place to build your Hilbert space. Okay, good. Okay, let me emphasize that the letter psi is everywhere on this slide. This algebra that I get is highly state dependent. That when I close this into the von Neumann algebra, I have to be working in a particular GNS Hilbert space. I had to subtract. When I constructed this abstract algebra, I had to subtract the 1-point functions in the state psi. So, there's a huge amount of state dependence in defining this algebra psi. And in particular, what this means is that it gives the idea of a fragmentation of the CFT Hilbert space at large n. Okay, so at finite n, any two states, psi and psi prime, in your particular finite n theory, they could have been connected by an element of this CFT algebra. I can just construct an operator in there that takes me from psi to psi prime. Okay, and so in a sense, the Hilbert space is completely connected. I can get between any two states using this algebra. But as n goes to infinity, these different semi-classical states are not connected by the single trace algebra. I can't get between them using only single trace operators. And it's not even clear if an overarching Hilbert space structure exists that encompasses all of the different semi-classical states in the strict n goes to infinity limit. And so you can think about this because the number of local degrees of freedom in the CFT was growing to be very large. And in a sense, the number of states as I'm increasing n is growing far too rapidly for there to be a sort of separable Hilbert space structure that encompasses all of these states at n equals infinity. And instead, what happens is that the Hilbert space sort of breaks up into these sort of disjoint continents of Hilbert spaces that are built, these GNS Hilbert spaces that are built around different semi-classical states. Okay, good. So let me give an example of this back to the sort of thermofield double that we discussed near the beginning. So in this case, we have two copies of the theory. We have a right and a left copy of the holographic theory. They each have their own single trace algebra, and let's consider the state to be the thermofield double. There are two possibilities depending on the temperature of this thermofield double. And one possibility is that if we're below this critical temperature, then the algebras that I get by doing this construction are what's called type 1 von Neumann algebras, like the familiar algebras of quantum mechanics. Whereas if I'm above the critical temperature, I should have put a temperature for this thermofield double. If we're above the critical temperature, then these large N algebras that I define are actually of type 3-1. Okay, and so we'll come back to that in a moment. Let me just describe what's going on in the bulk. So far I've just been talking about how do we talk about the large N limit of the CFT. Okay, now the bulk Hilbert space, now we're interested here in this sort of semi-classical limit. So, you know, we don't have complete definitions that we completely understand non-perturbatively in all the parameters of quantum gravity. But imagine that I had a quantum gravity theory that had a bunch of states, maybe a state psi. Then what's believed is that, you know, if I could define that theory for all the parameters Gn and H bar, finite, and those kind of things, in the limit that G Newton goes to 0, the physics can be effectively described by a classical solution of Einstein's equation. So this is how this is sort of getting us back to what we know from the quantum gravity theory. And if we then quantize perturbations of the bulk fields around the solution, we get a bulk Hilbert space. And what I want to say is that, you know, in general, even though of course we don't know this procedure, how do we go from quantum gravity psi defined in some non-perturbative theory to the classical solution? It's believed that you know, these different states should define different classical solution, so this construction will depend on the state psi. The algebra of bulk field perturbations is then just the set of all these it's just the algebra generated by all of those perturbations that are quantized in this bulk Hilbert space. And so I'll denote that by m tilde psi. Okay. And so what does ADS-CFT say in the semi-classical limit? Well, it says that when we take this G Newton to 0 limit or n to infinity limit on the boundary, this implies that the small perturbations around the background classical solution, which generates some Hilbert space, those are actually dual to this Gelfand-Neymark-Siegel Hilbert space that we built on the boundary using the large N algebras. So this is the sort of the statement of the duality, really in this strict limit. In particular, this means that those operator algebras must be identified. The algebra of bulk field perturbations must be identified with the single trace single trace operator algebra that we get in the large N limit on the CFT side. And let me just say, this is a familiar statement. This is the statement of so-called global reconstruction. If you give me access to the entire boundary, so here I've always been talking about single trace operators on the entire boundary. If you give me access to all of those single trace operators, then I can tell you I can tell you about all of the bulk field perturbations anywhere in the bulk. This is the statement of global reconstruction. Okay, and so how does this duality play out in the example of the thermofield double that we've been considering? So again, back to this example. Remember, I told you that from the large N, the analysis of these large N algebras in the CFT, we had this sort of phase transition between type 1 and type 3. How does that work in the bulk? Well, in the bulk, if we're below the so-called Hawking-Page phase transition, then these algebras are type 1, and that's precisely because the single trace operator algebras are dual to small excitations about a global ADS spacetime, and you know those states may be entangled in this thermofield double state. So this is the thermal ADS. But there's sort of no geometric realization of that entanglement. And in particular, these algebras are of type 1. And so this is sort of this dominant saddle below the Hawking-Page transition. If we're above the Hawking-Page transition, those algebras are type 3-1 from the boundary perspective. How is that reflected in the bulk? Well, it's reflected that now the dominant saddle is this eternal ADS black hole. And in particular, now these ML and MR algebras are dual to the algebras of operators in the right and left exterior of this black hole. Those are algebras in the semi-classical limit of quantum fields in curved space restricted to a subregion, and they're type 3-1 algebras. Okay, so that's sort of this gives a geometric interpretation of the fact that we found that the large N algebras were of type 3.1 above some critical temperature. And so this is sort of one of the themes of the talk, is the idea that the bulk gives a geometric interpretation of unexpected properties of the large N algebras. Okay, great. So far, yeah.
Are you going to elaborate on the conclusion? These are type 1 and type 3.1 from the point of view of the field theory here.
No, I wasn't going to elaborate on that, but roughly it has to do with, so everything in the large N algebra was determined by that, the algebra was completely determined by that commutator function, the C number that I get there. And when that commutator function has a particular support properties in terms of the boundary energy, that's what distinguishes between these type 1 and type 3. Yeah. Yeah.
For the fragmentation of the Hilbert space, the CFT perspective, into like just look at it as coming from different. You get something like free field theory, like straight. I mean, bit of equalization.
Yeah, right. So from the CFT perspective, the picture that we would have in mind, right, is that okay, all of those states are we have one Hilbert space structure at any finite n. But we have various states that might satisfy large N factorization. And what really happens is that there will be very small matrix elements of single trace operators going from some semi-classical state psi 1 to some other semi-classical state psi 2. Though they will have non-zero matrix elements of single trace operators at finite n, but those will be exponentially suppressed. And so when n goes to infinity, they literally separate into disjoint Hilbert spaces. Yeah.
How do you see the exponential rather than just power law?
That's a good question. Yeah, okay, I should have been more careful saying that. That's what we expect from these sort of bulk Euclidean path integral results. Yeah, so from the boundary perspective, I don't have a good, argument. Good, yeah, thanks. Okay, good. So if all these global algebras are identified, there must be an identification of sub-algebras. Okay, so let me come to that now. So if these global algebras are identified, I must have some mapping from sub-algebras on the boundary side to sub-algebras on the bulk side. In the semi-classical limit, the bulk theory is really just quantum fields on a fixed curve space-time background. And in particular, the algebras in that kind of theory, have a very specific structure that's constrained from causality in the bulk and the existence of an equation, a local equation of motion for the bulk theory. Okay, we want to understand how does the boundary theory reproduce the special structure of the bulk algebras? Okay, so just to emphasize that the bulk has this special structure, remember that the local bulk EFT is some quantum field theory on curved space. This means that the full algebra of bulk fields can be defined on a single Cauchy slice, or a neighborhood of a Cauchy slice. And then what I can do is use the local equation of motion to evolve all the operators back to a single Cauchy slice. But what I can do is, because it's a local theory, I can assign operator algebras to different regions of that Cauchy slice. So here I have the global algebra and this whole green disk here of operators that I get in the local bulk EFT. But the fact that it's a local theory means that I can sort of cut this slice up into regions and assign local algebras to each of those subregions. And in particular, to each one of these subregions, there will be a type 3.1 von Neumann algebra assigned. Okay, so that's the structure of the local bulk EFT. And so how is it possible that the boundary theory reproduces this? Well, here we need to think about how do the single trace operators behave at large n. So let's just consider some single trace operator like this. At finite n, we have the following relations. We have a Heisenberg equation of motion with the CFT Hamiltonian H that tells us if I want to know the single trace operator at a late time, solve that equation of motion in this way. Equivalent, or in another way to say it, is that we have a complete set of operators defined on the t=0 slice of the CFT, and we can just give some expansion of this time-evolved operator as some time-dependent coefficients times that complete basis of operators. Okay, but crucially, this will involve multi-trace CFT operators. And so what this means is that when we take n to infinity, this operator v of t can still be defined in the n to infinity limit through the limits of its correlation functions in appropriate states, but these equations no longer hold. So, for example, this h has some leading n in it that prevents this equation from being true. And moreover, the mixing here, this involves a mixing with operators that do not have well-defined large n limits. So v of t still exists, but its relations to operators on the t equals 0 slice are no longer there in the large n limit. And this can all be summarized by the fact that the single trace operator algebra, and remember that I also have this very simple algebra of commutators where they factorized, where the commutators were just some complex number. And it's generally known that algebra is what's called a generalized free field theory. Generalized free field theories are very strange for the following reason. So usually in quantum field theory, if I consider some causally complete diamond like this, then I can just use the equation of motion to evolve all of my operators back to whatever partial Cauchy slice that I have here, so A2 or A1, and I can use that to show that those two algebras are the same. But for generalized free field theory, this is not true because there's no local equation of motion that's obeyed by the operators themselves. That's sort of, that's the large unlimit of the fact that the single trace operators don't obey an equation of motion amongst only themselves. Okay. And so just to hammer this home, let me say that if I consider a causally incomplete region like this intersection of two diamonds, and that I haven't causally completed, that actually has a non-trivial algebra in the large n limit. So usually I would have said, well, evolve the operators back to this Cauchy slice, and then the algebra should be equivalent to the algebra of this bigger diamond. But at large n, this region and this region have distinct type 3-1 von Neumann algebras assigned to them. Okay. So in the global picture, what this is saying is that really those those bulk operators on this Cauchy slice of the bulk were equivalent to the single trace operators on the entire boundary spacetime. That was what they were dual to. Okay. And so because we get all of these additional type 3-1 algebras that emerge in the large n limit, this gives us a chance of describing local bulk physics local physics in the bulk. Okay, so as I've emphasized, we get a bunch more type 3-1 algebras that appear when we take the large n limit. And on the gravity side, we expect that there should be a type 3-1 algebra for any causally complete subregion of the bulk. And so the fact that we get all these additional CFT algebras in the large n limit of the CFT is very promising for there to be a duality. And so what we propose is that the algebra of local bulk operators in any causally complete bulk subregion is dual in this sense here to an emergent type 3-1 subalgebra in the large n limit of the CFT. I.e., I can find a von Neumann algebra in the bulk of bulk fields restricted to that subregion. And for any such algebra, I should be able to find a type 3-1 algebra on the boundary that has the same operator content. And let me say, this is a generalization of the usual RT surface formulation of subregion-subregion duality. Because we're not going to demand that the boundary algebras are associated to spatial subregions of a Cauchy slice on the boundary. We're going to allow for more general boundary subalgebras. Okay, there are, and so as I mentioned earlier in the talk that I would get to this, there are sort of two natural subalgebras that I can associate to any boundary spacetime subregion. And so this is how this connects to the idea of subregion-subregion duality. So imagine that R is sort of the neighborhood of this Cauchy slice of the diamond here, this blue line. There are two ways that I can construct a large n algebra, a large n algebra in this picture. The first way is that just within the CFT, I can restrict to all of the CFT operators that are supported in this neighborhood of this blue line here. And that defines for me some CFT subalgebra that's of type 3-1. And then I can ask, what are the operators in that subalgebra that survive the large n limit about the state psi, in the sense that their correlation functions, their endpoint functions are well defined in the state psi. So I have some subset of operators, and I can ask, okay, what are the operators that do that? And let me define that to be this algebra XR. So this is an algebra that's defined at large n, but through this particular procedure of going to the finite end theory, restricting to a subregion, and then taking the large n limit. But there's another thing that I could do, which is just say, well, let's consider the entire boundary space-time.
Sorry,
Yes.
is that really well defined, the region at finite n, that was well defined?
Oh, yeah, this is a boundary region.
Oh, boundary, okay.
Yeah, sorry, this is a boundary region. So this is well defined finite n. Yeah. Good. Well, there's another procedure that I could do, which is the fact that I know that I'll get this generalized free field theory in the large in the large n limit, and so that realizes this sort of field theory on the entire boundary spacetime. So what I can do is just go to that generalized free field theory and restrict to the operators that are supported in the causal completion of this region, which I denote by r hat. So let me emphasize, there's sort of two different procedures here. In this procedure, I first restrict to a boundary subregion R, then I take the large n limit. In this procedure, I first take the large n limit to get my generalized free fields, and then restrict to this subregion R hat. And let me say that these actually can generate different large n algebras that are in a sense still associated to that boundary subregion R.
You said before that you have different type 3 algebras to different slices of the same.
Yeah, it's precisely related to that point that.
So talking associated algebra for the whole thing.
Oh, sorry.
I mean, if you have this diamond, right?
Right.
You said before, like the different slices you can associate this inside this diamond. You can associate different algebras.
Right. Yeah. So for different good. Yeah. Sorry. So for different slices of this diamond, if I take large n first and then look at different slices of the diamond, then I'll get distinct subalgebras. Whereas if I do this X procedure, where I look then, because then I'm sort of remembering the fact that I had a finite n theory. In that case, then the algebra that I construct for that Cauchy slice is the same as the algebra that I construct for that Cauchy slice. And so through this procedure, different R's, different Cauchy slices R will generate the same large n algebra, but they'll generate different algebras for this picture where I took large n first.
Not the same as the one from there is no choice of like Cauchy slice.
Yeah. There's no choice of Cauchy slice. Yeah. So here, this XR really should be thought of as being associated to the full causally complete region, not to a particular Cauchy slice. Yeah.
Same, really same, not isomorphic.
No, there I mean really same. Yeah. Good. Okay, great. One can give an explicit characterization using the sort of JLMS arguments for the modular flow to explicitly characterize this, sort of just the mathematical definition of these algebras, and using this X, assuming that the JLMS criterion, the equivalence of bulk and boundary modular flow holds. Okay, so by definition, this X algebra actually will contain the Y algebra, but in general, that's not true. And so we propose that this X algebra is dual to what's called the entanglement wedge, which is one proposition for what should be the bulk dual of this boundary region R in subregion duality. Well, YR is dual to the causal wedge. So the entanglement wedge is this region that's defined through a particular extremization procedure, and then one takes the domain of dependence of a homology hypersurface. The causal wedge is much more sort of simply defined. I take the region R hat, the causal completion of the boundary region, and I shoot my light rays back into the bulk, and I look at where they intersect the region that's both in the past and the future of that. That's the causal wedge. Okay, so let me just say we have a procedure to identify the bulk subregions that I won't go into detail. So you can write down this global reconstruction so that you get a handle on what you mean by X, what you mean by local operators in the bulk. I can compute an expansion, and so that's the only bulk input that I need. Then I can compute an expansion of the generalized free field in terms of modes in the algebra of interest, maybe XR, and modes in the commutant. Then I can compute a basis change from a global expansion to a local expansion. Finally, I plug that basis change back into my original global expansion of this bulk operator. And I ask, okay, for which of the points do I not see any of these commutant modes? I only see modes in the local algebra of interest. And this defines the bulk region via this boundary-only procedure without having to use the RT surface or any idea of entanglement entropy in order to define that. So this sort of gives a procedure directly in the continuum to define the bulk dual. Okay, So let me just say that, when you compute this, the examples work out fine. So for example, if I have a half space like this Rindler wedge, one can do this algebraic procedure to compute what's the bulk dual. And it's sort of exactly this half slice, this sort of half slice of Poincare ADS. Similarly, and let me say that in either procedure to construct the large N algebra, they agree in this case. That's precisely because the modular flow is local for a Rindler wedge. I can't generate any extra operators by doing modular flow. Modular flow of a single trace operator is just another single trace operator for this region. Similarly, for an interval, one can compute the algebras here, and one finds the usual sort of semicircle in the bulk. That's the dual. Again, for conformal theory, the modular flow for an interval is local, and so I actually don't get any additional operators by considering this X procedure versus this Y procedure. But what happens? So let me give you a non-trivial example. Consider two separated half spaces like this. So I want to consider the sort of the geometric union of that Rindler wedge and this Rindler wedge. And if I do that, then now the modular flow for that region is actually non-local. And so I can do the procedure where I take large N and I just restrict to this boundary subregion and ask what's the bulk dual. Well, the bulk dual turns out to be this sort of geometric union of the ADS Rindler wedges in the bulk. Whereas if I do the procedure, that uses the non-local modular flow, I get the entire exterior of this semicircle here. So this algebra you can show explicitly on the boundary contains extra operators that this algebra does not. In the bulk, that is geometrically reflected by the fact that I have access to degrees of freedom in this middle region here that I did not have access to before. Okay, and so this is an example. Where we can give this boundary algebraic calculation and show that the entanglement wedge exceeds the causal wedge in the bulk, which is precisely because this X algebra exceeds the Y algebra on the boundary. The two different large N limit procedures do not agree. Okay. So let me just say this is the first example of what's called the additivity anomaly. So we can ignore the first point. If we have two boundary subregions, we can ask what's the algebra assigned to the union of those subregions. And this V symbol, all this V symbol means is that I take the algebra assigned to this region R1, the algebra assigned to R2, and I construct the smallest von Neumann algebra that contains each of those constituent parts. Okay, so usually for so-called complete theories, this additivity property is satisfied, but this is actually violated in the large N limit. As a feature of the large N limit, this algebra that I get in this case can be larger than the algebra that I would get, but it's larger than the smallest possible von Neumann algebra that I get by using the two constituent parts. And so this is actually, we saw an example of this on the last slide, where that Y algebra I would obtain by constructing the smallest algebra containing sort of the right and the left Rindler wedges, whereas the X algebra did not have that property. Okay, and so this was noticed a long time ago in holography that the algebras were going to have to obey this structure, but we sort of explicitly gave a boundary calculation that shows that this is true. And there's been some recent discussion in the context of generalized symmetries that try to understand the nature of this anomaly. Okay, so let me skip this other example in the interest of time because it's basically the same. How do we understand general bulk subregions? So bulk subregions that are not bounded by the anchor by a boundary anchored extremal surface. So subregions that are not the entanglement wedge under some RT Ryu-Takanagi prescription for any subregion. Those are not described by subregion duality. So for example, a region like this pink region that I've drawn here is not described by subregion duality because this is not the entanglement wedge of any boundary subregion. But with subalgebras, we can describe much more general bulk subregions. And that's because we still have all of these extra algebras that I've tried to emphasize associated to non-causally complete boundary spacetime subregions. We have all of these extra algebras in the boundary. We can still restrict generalized free fields to that subregion and define a non-trivial von Neumann algebra. These are going to be dual to what's called the causal domain of R. Okay, and so let me just say, in particular, an example of it is something called these time bands. This is an example. A time band is just the region between two non-intersecting Cauchy slices. If you restrict single trace operators, you can show that you get a non-trivial boundary subalgebra. And you can actually use a generalization of the proof of what's called the time-like tube theorem in algebraic quantum field theory to explicitly show, to explicitly derive the bulk dual. So it's kind of interesting that in this work from the 60s, you can use that actually to derive bulk duals in ADS CFT. Okay, so for example, for this uniform time band, the bulk dual is a region like this. This is a bulk region that contains all near boundary points on a Cauchy slice and is not bounded by some extremal surface. On the Penrose diagram, it's this spherically symmetric region that looks like this, that's bounded by these time bands. Okay, good. Since this gives us a non-trivial algebra, the algebra of the complementary region can be given by the commutant, all of the operators that commute with that algebra. At finite n, this algebra of a time band, because it contains the neighborhood of a Cauchy slice, would have been the full algebra. And so its commutant would be trivial. And so this suggests that deep bulk subregions that have no near boundary points are purely emergent in the large n limit. They are features of the large n limit that come from sort of this violation of the so-called time slice axiom in the large n limit. So for example, in vacuum ADS, the algebra of a time band is dual to this region, and the algebra of this hole in ADS, as it's called, is the commutant of that. Okay, and since I'm way over time, let me sort of skip some applications, but let me just say, and you can ask me later, we can understand the quantum error correction picture of holography, why it's been so successful in this language. The picture that we get is actually slightly different from what you would say from quantum error correcting models. But what's crucial is the fact that information is delocalized. This additivity anomaly is in a sense this algebraic statement that information in the boundary theory is delocalized in the large n limit, and that precisely that delocalization is why quantum error correction models, which is what they take in as input, why they've been so successful at modeling these aspects like entanglement wedge reconstruction in ADS CFT. And finally, let me say that we can understand something called the connected wedge theorem in terms of algebraic language, but that would take way too long to describe, so let me skip that. Good. Okay, so coming back to these questions that we wanted to answer in the beginning, what did we understand from these large N algebras? Well, these space-time subregions are related to emergent type 3-1 algebras on the boundary. We can describe much more general space-time subregions now. Event horizons are related to particular properties of those type 3-1 algebras. One can construct infalling times from so-called half-sided modular inclusions, and feel free to ask me about that after if you're curious. And so let me close with some future directions. So really the most interesting aspect of this program, at least to me, is trying to understand how do we get all of these classical geometric features of the bulk space-time? How do those emerge from fundamentally quantum degrees of freedom that are living on the boundary in the conformal field theory? And so we've been able to understand many aspects of how that local bulk physics arises and how those geometric features of the bulk geometry arise, but there's still lots more to do. In particular, we believe that we can understand bulk volume differences between volumes of bulk subregions in terms of what's called an index of boundary algebra inclusions. And so there's just basically all I want to say is that there might be an algebraic definition of the bulk volume. And I think that would be very interesting to understand. One thing is that I talked mostly about the thermofield double. It'd be interesting to understand in the algebraic picture, how does the black hole interior come in for single-sided black holes? And in particular, since we can come up with these evolution operators that take you from outside of the black hole into the interior, is there some probe of the singularity that we can understand in this language? And that has proven very difficult, even though the singularity is, of course, a feature of the classical geometry. So you would hope that you see something about it in this limit. Good. Another question is, can we extend this by putting in appropriate corrections to understand the algebraic description of entanglement wedges that are now associated with non-trivial quantum extremal surfaces and islands? What I talked about at the end of the talk on Friday was the idea of these implications of 1/n perturbation theory and deformations to these type 2 algebras that have been discussed recently. I think there's still lots to understand there. How do we get these sort of information theoretic quantities out? And how do we sort of get back to the original type 1 picture of the CFT that's there at finite n, how do we get back to that from a bulk perspective? And that's some program that's underway that we still certainly don't fully understand. And then finally, in connection to these sort of space-time wormholes and the idea of null states that have been discussed recently and trying to give bulk descriptions of the Hilbert space, it'd be interesting to understand how those non-perturbative corrections deform the effective field theory algebras when we try to include those corrections in defining the effective field theory algebras. And is that enough to get back down to one of these type 1 algebras? I think is a very, very interesting question. And it's not clear to me at the moment. So with that, I apologize for going over, but thanks for your time.
So do you expect a finite index inclusions?
So that's the question. So let me say why maybe there is a finite index inclusion. And so I think generically, let's consider if you consider the index of an inclusion of a Rindler wedge and another Rindler wedge, almost certainly that index is going to be infinite. Okay, but in this setting, from the boundary perspective, the geometric these are different algebras. This Y algebra and this X algebra that I explained. Those algebras are associated to the same geometric boundary subregion. And so I think that gives you at least a hope that the extra operators that you have in that setting will give you a finite index inclusion, but this is definitely speculation.
Yeah, then you get a fusion category and stuff
Mm-hmm.
by module. It doesn't seem right. You should be getting like some wild category, not a good fusion category with finite number of objects.
Okay.
I mean, like what do we expect from holographic CFT? Like lots of objects. Lots of primary field check. That was really like a dream. And so, I'd like to discuss that after if you have ideas about it, of whether or not. Yeah. Okay. Yeah.
So you have this sort of page transition temperature for the algebra, but that's really because the algebra is associated with the state. So
Yes.
really the state that has the transition in a way, and then the operators are associated with it. I mean, it's hard to see how the operators would have the face.
Oh, right. So I think, so good. So certainly, I guess, the sort of the finite and genuine CFT operators themselves will not have some phase transition. But because we had to do this sort of song and dance to define what are the operators that survive the large N limit, and because that involved saying which set of states we're going to act on, that's how the operators know about that phase transition. Yeah.
Like that.
Yeah.
So what's the difference between the algebra, the boundary that corresponds to like the region inside or outside the black hole? There is some problem.
Oh, good. Right. So at least in the eternal black hole setting, in order to understand any sort of precisely because in order to define interior black hole operators in the black hole interior are causally connected to the left boundary, right? So this is roughly right. And so necessarily in this description, the algebra of operators that will include some part of the interior has to necessarily include some left operators in order basically for those commutators to ever be non-zero. And so in that setting, the difference is whether or not the algebra includes any left operators or not.
So if you want to look for islets and stuff like this.
That's good. So right. So I think for the island setting, what you would have to do is in the states that you're considering, this modular flow will have to we'll have to mix. We'll have to sort of mix you non-trivially with the bath in those settings in order to have access to those operators.
Yeah, okay, I mean, so the 1/n corrections, I mean, these are small, so, I mean, the whole structure here for it goes to infinity, doesn't it only gets perturbed a little bit if you were to go to the next to 1/n, it doesn't.
Good, yeah, so this, I think this whole structure still exists to any finite order in 1/n perturbation. And then
That's an expectation or based on?
based on the fact that, you can always sort of construct, in the bulk, you can always construct the corrections to sort of the HKL kernel to localize everything again. And so morally, there should be some boundary interpretation of those corrections. And they should not, I think they should not be able to deform you away from this sort of type 3-1 picture. But then, of course, going to all orders in 1/n is a different story. Yeah.
Yeah, let's thank Sam again.